example that I mentioned was, to imagine it was spring mass system, the easiest thing that you can imagine, the spring mass system. One end of a spring is fixed, other end is attached to a block of mass m, spring constant k, surface is smooth. Now if this object is displaced from its mean position and released, then it will execute simple harmonic motion. Suppose at some instant the particle is somewhere here, displaced from the mean position through a distance x. Suppose returning towards the mean position with speed v. What is the kinetic energy of this system? Not the block, the spring mass system. What is the kinetic energy?
Sir, half kx square.
I'm asking kinetic energy. Yes. Why this object is not moving? Why rest? We have displaced it from the mean position and then released. It is executing this to and fro motion, and at some instant the block is here. Is the block at rest or it is moving towards the mean position? So it possesses some speed. So it will have kinetic energy half mv square. And what is the potential energy of the system? Yes, you need to reply, otherwise we cannot proceed. Potential energy of the system, the spring mass system. What is the potential energy of a stretched spring? This is half kx square, potential energy of a stretched spring. What will be the total energy? T plus V. So you have this total energy as half mv square plus half kx square. If this is solved, what final answer will we will get?
Half mv square plus k square.
Pardon? Half?
mv square plus kx square.
That is simply added here. Actually, why I asked that what you will get is, you have an expression for x. I am taking the case that the particle was at the mean position at t equals to 0. So x is a sine of omega t and velocity is a omega cos of omega t. If you put these values here, you will get the answer as half k a square. You can calculate this. What was the formula for k that we have? K was equals to m into omega square. So this is m omega square a square. Now tell me, which quantity here is variable? M, omega or A? Which one is variable?
Sir, all are constant.
Yes, very correct. All are constant. None of the quantity is variable. All are constant, which means that the total energy of a harmonic oscillator is constant. Just make a reminder. When is the total energy constant?
For what type of system? For free vibration. When there is no damping force, friction is absent, then the total energy is constant. If a friction would have been present, then if you displace it and then release, the amplitude will keep on decreasing and finally the particle will stop under the influence of the damping force. But I repeatedly mentioned that right now we are going to discuss free vibration where there is no damping force. So this is the expression for kinetic energy. This is the expression for potential energy. Uh, what was the formula that I told you? How to express V in terms of X? What was V in terms of X?
Omega under root a square minus x square.
Correct. If I put it here, what will be the value? Half m omega square. Then I have a square minus x square. And the potential energy is half m omega square x square. Do remember this. This is very required. Half m omega square x square. Just final thing that I discuss. Suppose in this axis you have x and in this axis you have energy. This axis is energy and this axis is x. This is x, this is energy. Suppose this is potential energy. How will potential energy vary with x? How will the potential energy vary with x? You have the equation.
Sir, parabolic.
Parabolic.
Sir, upward parabola passing through the origin.
Yes, the vertex touching the origin. Na?
Yes, sir.
Yes, sir.
That means you have something like this. Yes, we have something like this. We have something like this. Suppose this is the potential energy curve. The potential energy is maximum at the extreme and minimum at 0. This is the variation of potential energy. What about the kinetic energy?
So maximum at the mean position and minimum at the extreme position.
Very true. Just the reverse parabola. Is it like this? This is our potential energy curve, V as a function of x. And this is our kinetic energy curve, T as a function of x. The kinetic energy is maximum at the mean position. But is it that the total energy is constant?
Yes, sir. In this case, it is constant.
It is constant. So, what is the potential energy at x equals to 0?
0.
0. And the kinetic energy is maximum.
Yes, sir.
So, at x equals to 0, you have potential energy as 0 and you have kinetic energy maximum, and that maximum kinetic energy will be half m omega square a square. You can verify from the equation also. This is kinetic energy. At x equals to 0, this terms becomes 0 and you have half m omega square a square, isn't it? Half m omega square a square. At the extreme, that is at x equals to plus or minus a, what is the kinetic energy?
0.
0. And what is the potential energy?
Maximum.
Half, correct, m omega square a square. What is the total energy at x equals to 0? Total energy at x equals to 0? What is the total energy at extreme? Same. You take any point, you take any of the point, like you take this position. Isn't it that at this position, both potential energy and kinetic energy are equal?
Yes, sir.
Yes. But you add, the total energy will be half m omega square a square. Somewhere here, you have more kinetic energy and less potential energy. You have more kinetic energy and less potential energy. But the total energy will be half m omega square a square. So at any position, the total energy is constant. They are just sharing, they are being just shared between the kinetic energy and the potential energy. We also wrote it here that the total energy is constant and that is equals to half m omega square a square. Fine. Now, just you remember the two things that we discussed, either the potential step we discussed or the potential barrier that we discussed. The potential step that we discussed or the potential barrier that we discussed. This is x equals to 0. Suppose this is x equals to 0 and this is x equals to a. The potential energy here was V naught and the potential energy here was 0. What is the general Schrodinger equation that we have? Time independent one, d2 psi by dx square plus 2m by h cut square e minus v psi is equals to 0. So what will be the Schrodinger equation for this region? Yes, you need to reply. d2 psi by dx square plus 2m by h cut square. बोलो, इस जगह का श्रोडिंगर इक्वेशन लिखना है.
E psi
V becomes 0, so you have E psi equal to.
0.
What about the Schrodinger equation here? d2
d2
psi
psi
by
by dx square
plus
plus 2m by h cut square E minus V naught psi equals to 0.
0. Similarly, we have wrote the Schrodinger's equation for this potential barrier also. I hope you can correlate now. Now, where these two representing the variation of potential energy with x, this one and this one.
Yes, sir.
Yes. Now, for a harmonic oscillator, the variation of potential energy with x, which you just now have told me that it is a parabola. This is how the potential energy of a harmonic oscillator varies with x. This is V and this is x. Now suppose I want to write the Schrodinger equation for a linear harmonic oscillator. It is d2 psi by dx square plus 2m by h cut square. Then you have e minus v function of x operating on psi, which is also function of x, is 0. Agree, everyone? d2 psi by dx square plus 2m by h cut square. This is e minus, what is the value of vx?
Half m omega square x square.
Half m omega square x square operating on psi equal to 0. So this is the Schrodinger equation for a linear harmonic oscillator. Now, what difference will you feel with the previous one is that in this equation, is it that this entire term is constant?
Yes, sir.
तो क्या करते थे, याद करो, इसको लिख देते थे k स्क्वायर. Now here, is this entire term constant again?
Yes, sir.
तो इसको कुछ और नाम दे दिए थे शायद अल्फा स्क्वायर. Now you come to this Schrodinger equation for a harmonic oscillator. Is this term constant?
No, sir.
No. So I cannot substitute this by a constant like k, alpha, gamma, beta or anything. So here lies the difference between solving the Schrodinger equation for a harmonic oscillator and the Schrodinger equations that we solved for a potential step or potential barrier. I hope this part is clear.
Yes, sir.
ठीक है? Anyone, any query, any doubt?
No, sir.
So you have understand that definitely the method of solving the Schrodinger equation for a harmonic oscillator will be different, will be a bit difficult also, because the coefficient of psi is not constant this time. Previously, what we were finding, what we were handling, the coefficients used to be constant. So because this is a variable situation, so once you start solving this, you will ultimately learn that after solving a few steps, this equation will result into a Hermite polynomial. हम इसको सॉल्व करेंगे तो हमको मिलेगा कि ये इक्वेशन अल्टीमेटली हर्माइट पॉलिनोमियल के साथ मैच करेगा. जैसे ही ये हर्माइट पॉलिनोमियल के साथ मैच करेगा तो हम हर्माइट डिफरेंशियल इक्वेशन का जो स्टैंडर्ड सॉल्यूशन है उसको ले लेंगे. The only reason is that because these are series solution, so even though you have not studied Hermite equation, but you know that solving Legender's equation and solving Bessel's equation involves a lot of calculation because they are not straightforward differential equation. We use that Fibonacci's method for solving them. So here we will skip the solution. I'm not bothered how to solve Hermite equation. We will take the standard solution of Hermite equation. And we will more focus on the interpretation of the wave functions. They will be meaningful, and because you are having the classes for that Skylab, MATLAB also, so you will be able to plot these wave functions by writing the program for that wave function. So let us start with this. The very common parts, we will discuss it quickly. A particle executing to and fro motion about a mean position is a simple harmonic oscillator. We need to find the eigenvalues and eigenfunctions of a 1D harmonic oscillator. 1D मतलब ही linear harmonic हो गया. Is a linear harmonic oscillator. The potential, yeah. नहीं, श्रोडिंजर इक्वेशन में ही तो E माइनस भी है, वहां तो हम V का ही वैल्यू पुट करेंगे. और ऐसे भी E माइनस भी इज अगेन काइनेटिक एनर्जी. So you can put the kinetic energy, but even the kinetic energy is also not constant. Half mv square. The V involved in harmonic oscillator is varying. 0 at the extreme and maximum at the mean position. So if you wish to take the kinetic energy, you can take it, but still the process will be same. Now Schrodinger time, this one. The potential energy of a harmonic oscillator, as we have already discussed, half kx square. The value of k is m omega square x square. So the Hamiltonian is this, and this is the Schrodinger equation. H psi equal to E psi. So this up to this we have already discussed. देखो तो है ना, d2 psi by dx square plus 2m by h cut square E minus, we have substituted the value of the potential energy, and that all equated to 0. Now comes the mathematics. how to solve this. So some manipulations are to be done to convert it into a known differential equation. We always try this because solving an unknown equation will be more tedious. So it is tried to that can we transform this equation to some known format of the differential equation so that I can use the standard results of that differential equation. So what is done here? It is convenient to write the above equation in terms of dimensionless quantities. So what is to be done here? Alpha times x is to be written as zeta. What is alpha? I will discuss here. Alpha times x is to be written as zeta. If it is so, then you differentiate both sides. Do remember that this, can anyone tell me what will be the unit of alpha? Now, see this line. It is convenient to write the above equation in terms of dimensionless quantities. So this zeta is dimensionless. So alpha must have the unit of 1 by length. That will make zeta a unitless quantity. So alpha is something which has the dimensions of inverse of length. So the variable here is x, and we are trying to transform the equation into some dimensionless quantities. Uh, can you understand this equation? Basically, we are converting the variable x to a new variable zeta. X, we are converting it to a new variable. So nothing specific. What is done here is, suppose you have this term d psi by dx. So you have this term d psi by dx. We are trying to convert the variable x into zeta. We have supposed a relation that zeta is alpha times x. So can we write this as d psi by dx? Sorry, d psi by d zeta into d zeta by dx.
Yes, sir.
Leave it as it is, d psi by d zeta into d by dx of zeta is alpha x. So the term that will survive is alpha. So it is alpha d psi by dx. This is the value of d psi by dx. But actually, the equation involves the second order differential d2 psi by dx square. So this is like d psi by dx, again differentiated with respect to x. Now this d psi by dx can be again written as d by d zeta into d zeta by dx, and into d psi by dx is alpha d psi by d zeta. It is d psi by d zeta. Again, what is the value of this one?
Alpha.
Alpha.
So it is like alpha square d2 psi by d zeta square. This is the value of d2 psi by dx square. बीच का स्टेप्स थोड़ा थोड़ा हटाया हुआ है. d2 psi by dx square is alpha square d2 psi by d zeta square. We have calculated this one, this one, this one. For this I will substitute this one. So substituting this one, you see, इसके जगह पर ई वाला टर्म लिख दिया. Now what about the other terms? 2m by h cut square e minus half m omega square. We are converting x into zeta. So x has been substituted as zeta by alpha. So it is zeta square by alpha square. यहाँ तक okay?
Yes, sir.
Yes, sir.
Now this is same, just we have divided throughout by alpha square. तो यहाँ से alpha square eliminate हो गया. The first term is 2me by h cut square into alpha square. The second term is half m omega square zeta square by alpha square multiplied by 2m divided by h cut square, और एक और अल्फा स्क्वायर से डिवाइड हुआ है, so that makes it alpha to the power 4. So this is the equation. Further some substitutions are made. 2me divided by h cut square alpha square will be written as lambda, and this m square omega square by h cut square alpha to the power 4 is taken as 1. Remember, this lambda is also a dimensionless quantity. Zeta dimensionless, lambda dimensionless. We were trying to convert the equation in terms of zeta and dimensionless quantities lambda and zeta. So you have something like alpha is equals to m omega by h cut. The constant that we defined, that zeta is proportional to x. So zeta is alpha times x. This is the value of alpha, which is under root m omega by h cut. And from the other section you have this 2m e by h cut omega as lambda. This is something that we will require because this contains E. This will give you the energy eigenvalues. You are getting the mathematics? Now, let us return back to the equation where we are substituting this one. This is written as it is. Now, this entire thing has been substituted by lambda. तो इसके जगह पर हमने lambda लिखा. ये पूरा फ्रैक्शन 1 लिया गया है, तो दैट इज 1 and zeta square psi is equals to 0. Remember that these substitutions are again being made to convert the equation into some known differential equation. Just for example, that in these equations, if you see this 2me divided by h cut square, okay, it is constant. You could have substituted this as k also, but this is written as k square only for the purpose that the differential equation will be easier to solve. 2me by h cut square constant है, k लिख सकते थे, लेकिन k स्क्वायर सिर्फ इसलिए लिख देते हैं जिससे कि ऐसा डिफरेंशियल इक्वेशन बनेगा जिसका कि सॉल्यूशन आइदर नोन है या उसको सॉल्व करना इजी है? सो दिस इज द इक्वेशन. यस, यहां तक आने के बाद एक बार आगे चलेंगे. हाँ, यहां तक बोलिए, रिप्लाई करिए. ठीक है.
यस सर.
अगेन ये ठीक ही बात है. लाइक दिस एम ओमेगा स्क्वायर एच कट स्क्वायर बाई अल्फा, ये पूरा क्वांटिटी को 1 लेने का पर्पस अगेन सेम वही है कि हम इसको ले जाना जा रहे हैं टुवर्ड्स हर्माइट इक्वेशन. तो होता क्या कि अगर आप हर्माइट पढ़े रहेंगे तो आपको ये ज्यादा कन्वीनियंटली समझ में आएगा कि ये सब्स्टिट्यूशन क्यों ले रहे हैं. बट ओके फाइन. अभी हाँ, वन से अलग हो सकता है. अब इसमें क्या होगा, देखो, वेरी करेक्ट, ये 1 से अलग हो सकता है, लेकिन जब इसको 1 ले रहे हैं तो इसके 1 के अकॉर्डिंग हमको किसका वैल्यू निकल के आ रहा है? अल्फा का. और ये जो अल्फा का वैल्यू है, ये अल्फा का वैल्यू ये अल्फा का वैल्यू जीटा के साथ कोरिलेट कर रहे हैं. तो ये 1 लेने से ये सब अकॉर्डिंगली एडजस्ट हो जाएगा. इसको कुछ और भी कांस्टेंट लेते तो भी वो अकॉर्डिंगली एडजस्ट होगा. समझ पाए क्या बोले? वैल्यूज अकॉर्डिंगली एडजस्ट होगा उसके साथ. अच्छा ठीक है, इसको थोड़ा देर के लिए, क्वेश्चन एकदम जेन्युइन है, इसको थोड़ा देर के लिए माइंड में रखिए. आंसर को दोबारा पढ़ते समय हो सकता है आपको थोड़ा और क्लैरिटी आएगा. वंस वी टच द हर्माइट इक्वेशन, देन वी विल रिटर्न बैक. नाउ this is the equation that you are left with. Yes. Now because there is only one variable, that is why we have converted this total differential equation into partial or partial into total. Any one you can do. Now again lies the problem that this coefficient is not constant. This coefficient is not constant. The problem is still there. The equation that we used to study earlier was d2 psi by dx square plus k square psi is equals to 0. These were the equations we were initially discussing. Psi is a function of x. Psi is function of x. ये वाला x और ये वाला x एक ही चीज है, लेकिन इस k के अंदर कोई x का टर्म प्रेजेंट नहीं है. लेकिन अभी का इक्वेशन में देखिए, psi इज फंक्शन ऑफ जीटा, psi इज फंक्शन ऑफ जीटा, लेकिन इस कोफिशिएंट में भी जीटा प्रेजेंट है. ठीक है. सो कीप दैट इन माइंड. We first analyze the behavior of psi in the asymptotic region where mod zeta tends to 0. For any finite value of total energy E, the quantity lambda becomes negligible with respect to zeta in the limit when zeta tends to infinity. In this limit, the equation 3 becomes. Okay, यहाँ पर थोड़ा सा फोकस करिए. We first analyze the behavior of psi in the asymptotic region. Asymptotic region, suppose this is our x-axis. Initially we had this where we have written the potential energy term. Suppose this potential energy is function of x and this is also x. Now, zeta has been now written as alpha into x. So when x tends to infinity, that means at very far away from the mean position, zeta will also tend to infinity.
Yes, sir.
Sir.
तो asymptotic वर्ड इसीलिए यूज कर रहे हैं कि that means approaching towards a large distance from the mean position. So let us first analyze the behavior of psi in the asymptotic region. हम psi का behavior सोच रहे हैं asymptotic region में, मतलब extremes के आसपास psi का behavior सोच रहे हैं. That is when zeta tends to, ये गलत लिख दिया है लग रहा है, देखो तो zeta tends to infinity होगा ना.
Yes, sir. Infinity.
Yes, sir.
It will be zeta tending to infinity for any finite value of total energy. So if zeta tends to infinity, when zeta tends to infinity, lambda can be neglected as compared to zeta square. Yes.
Yes, sir.
And if so, then the equation will look like this.
Yes, sir.
Yes. तो इसमें इस बात का ध्यान रखना कि अभी जो सॉल्यूशन हम लिखने जा रहे हैं जस्ट नाउ, वो लेकिन तभी वैलिड होगा जब x या जीटा टेंड करेगा टुवर्ड्स इंफिनिटी, टुवर्ड्स द एक्सट्रीम ये होल्ड करेगा, नॉट क्लोज टू द मीन पोजीशन. बोला ठीक है, फिर भी लेट अस फाइंड सम सॉल्यूशन. In quantum mechanics, many a times you will not get the exact solution. So let us start with this. For large enough zeta, it can be readily verified that psi zeta will have a format like this. मतलब ये बोल सकते हो कि इस इक्वेशन का ऐसा सॉल्यूशन होगा, यही बोला जा रहा है. For large enough zeta, for large values of x, for large values of zeta, that means far away from the mean position, the wave function will take a format like this. अच्छा, ये कुछ लॉजिक के साथ ही लिखा गया है, सॉल्व नहीं किए हैं, कुछ लॉजिक के साथ लिखा गया है और सारा लॉजिक इसी में है. किसका वैल्यू लिख रहे हो? साई जीटा, मैंने वेव फंक्शन को लिख रहे हैं. और वेव फंक्शन कैसा लिए हैं? तो प्लस माइनस जीटा स्क्वायर बाई 2, प्लस माइनस जीटा स्क्वायर बाई 2. प्लस माइनस जीटा स्क्वायर बाई 2 में से पहले माइनस जीटा स्क्वायर बाई 2 के बारे में सोचिए. माइनस जीटा स्क्वायर बाई 2 के बारे में सोचेंगे. माइनस जीटा स्क्वायर बाई 2 के बारे में सोचेंगे मतलब क्या हम लोग सोच रहे हैं? सी, think about the wave function psi as a function of zeta, and instead of x we are having the variable zeta. When zeta tends to infinity, what property should psi satisfy?
Psi should vanish.
Yes, when zeta tends to infinity, psi zeta should vanish. It should not become infinity. So the possible type of solution is that it should exponentially decay. Then only when zeta will increase, psi will tend something towards 0, because it has to satisfy the property should vanish at infinity. So this is a possible solution. Yes, there are some mathematics involved, but as I mentioned that I will skip the mathematics because the physics part itself is a bit lengthy. So we cannot enter into every solution part. So I'm just trying to make you imagine that what may be happening. So you have something. Now this constant is also not a constant. It is a function of zeta. Zeta to the power some value. It may be 2, 3, 4, anything. And then exponential plus or minus zeta square by 2. The variation is something like this. This has been solved by some mathematics. And we are writing this solution. Now, this is solution of equation 4. So obviously, this will satisfy equation 4. So this equation satisfies equation 4. So for the leading terms are concerned and p has any finite value. Because the wave function must be bounded everywhere, including at zeta equals to plus or minus infinity, the physically acceptable solution must contain only the negative sign in the exponent. The asymptotic analysis therefore suggests that the solution of equation 3, which are valid for all values of zeta, must have the form. This is psi zeta is exponential minus zeta square by 2, and this has been referred to as some term h with index zeta. That means h is some variable term depending upon zeta. प्लस क्यों हट गया? आई होप ये समझ आया. बोलो. नहीं समझ रहा तो भी डिस्कस करेंगे. ऑनलाइन में है तो पूछना नहीं, ऐसा नहीं है. प्लस टर्म क्यों हट गया, ये क्लियर हुआ? विष्णु बोलो, प्लस टर्म क्यों हटा, समझ आया?
नो सर, एक बार एक्सप्लेन कर दीजिए.
प्लस टर्म हटने का रीजन बहुत सीधा ही है. आप लोग बहुत फोकस्ड नहीं सुने होंगे. द ओनली रिक्वायरमेंट इज that when zeta tends to infinity, psi zeta must tend to
0.
If you take this term exponential plus zeta square by 2, so when zeta will tend to infinity, if this is positive, then the wave function will also tend to infinity.
Infinity.
Psi zeta is proportional to exponential plus zeta square by 2. If you have a format like this, then when zeta will tend to infinity, psi zeta will also tend to infinity, which is not allowed. But if you take the exponential negative, then you have a valid wave function that as when zeta tends to infinity, the wave function tends to 0. Is it now okay? Where h zeta are functions which must not affect the asymptotic behavior of psi. मतलब ये कोई ऐसा वैल्यू होगा जो इसके asymptotic behavior को affect नहीं करेगा. मतलब जीटा टेंडिंग टू इंफिनिटी पर वेव फंक्शन 0 फिर भी आएगा, इसका कोई भी वैल्यू हो. Substituting 5, this is the solution that we have in equation 3. In equation 3, this one, we get the differential equation like this. इस इक्वेशन को जो सॉल्यूशन है हमारा, लेकिन ये सॉल्यूशन सिर्फ कहां पर होल्ड करेगा? when zeta tends to infinity. लेकिन हमको सिर्फ zeta tend to infinity का सॉल्यूशन से काम नहीं है. हमको तो पूरा जीटा के लिए या पूरा x के लिए सॉल्यूशन चाहिए. तो क्या किया गया? एसिम्प्टोटिक सॉल्यूशन जो आया उसको हमने यहां पुट किया, और पुट करके सॉल्व करोगे तो ऐसा कुछ इक्वेशन आएगा. ये मैथमेटिक्स आप करके देख सकते हैं, नथिंग डिफिकल्ट. वी आर जस्ट putting this value, we are just putting this value of psi here. यहाँ पर इसको put कर देंगे psi को यहाँ put कर देंगे, and then you solve, you will get this equation. d2h by d zeta square minus 2 zeta dh by d zeta plus lambda minus 1 is equals to 0. Okay. Now almost mathematics is done, almost is done, but yes, I'm acknowledging the fact that we have not discussed every details of the mathematics involved here. We have just taken a few required solutions, etc. Now, if anyone is a little bit familiar with Hermite equation generally has this type of format: d2y by dx square minus 2x dy by dx plus y is equals to 0. हर्माइट इक्वेशन में खाली थोड़ा सा एक डिफरेंस होता है, यहां पर एक 2n होता है. दिस इज द एग्जैक्ट फॉर्मेट ऑफ हर्माइट इक्वेशन. ये हर्माइट इक्वेशन है.
Yes, sir.
तो ये जो इक्वेशन है, ये एग्जैक्ट हर्माइट इक्वेशन में फिट हो जाएगा इफ यू टेक लैम्डा माइनस 1 इक्वल्स टू 2n. आप ऐसा लीजिएगा तो ये एग्जैक्ट हर्माइट इक्वेशन में फिट कर जाएगा. आपने क्योंकि ये फॉबिनासिस मेथड पढ़ा है, सो what you must be knowing that this type of equations cannot be solved by general method because they contains some singularities. मतलब x के किसी वैल्यू पर वेव फंक्शन अनडिफाइंड हो जाता है, सिंगुलरिटी पॉइंट एग्जिस्ट करता है, इसलिए इसको नॉर्मल मेथड से सॉल्व नहीं कर पाते हैं, तो हम लोग सीरीज सॉल्यूशन मेथड पे जाते हैं. सो एज आई मेंशन्ड दैट आई विल नॉट एंटर इनटू द सीरीज सॉल्यूशन. सो क्या हमने बोला कि ये बन जाएगा हर्माइट इक्वेशन कब? जब लैम्डा माइनस 1 की वैल्यू 2n. देखो lambda minus 1 is 2n. Now only when lambda minus 1 is equals to 2n, then only the solution of equation 6 will be well behaved at x equals to plus minus infinity. जब lambda minus 1 2n होगा तो ही उसका asymptotic solution होल्ड करता रहेगा. अदरवाइज x इक्वल्स टू इंफिनिटी पर या जीटा इक्वल्स टू इंफिनिटी पर जो वेव फंक्शन है वो थोड़ा सा इनवैलिड आने लगेगा. So if you take lambda minus 1 as 2n, then you have lambda is equals to 2n plus 1, and initially somewhere we have substituted 2e by h cut omega as lambda. So 2e by h cut omega as lambda will give you e equals to 2n plus 1 h omega by 2. This will basically give you e equals to n plus half h cut omega. In this Hermite equation, where you write this lambda minus 1 as 2n, or this 2n, n takes the value 0, 1, 2, and so on. These are the values of 2n in the Hermite equation. N is equals to 0, 1, 2, 3, and so on. Now, because for a different n, you have a different e. So we have by ourselves substituted, put a mandatory suffix en. So now with different values of n, will I get a different value of e?
Yes, sir.
So these are the energy eigenvalues of a harmonic oscillator. You must remember that h cut omega represents energy. H nu or h cut omega both represents energy. So n plus half h cut omega. There is a minimum term that I will discuss. Now, again, this is just a formality type of thing because we are not actually discussing the exact solution, but to have a view of that so that we are able to analyze the wave function. At least we are trying to give you a little bit of mathematics. Now the physically acceptable solution uh, of equation 3 corresponds to the eigenvalues given by, if you return back here, आपको दिखेगा कि हमने सॉल्यूशन कुछ इस टाइप का लिखा था, ठीक है, लेकिन हमको मिला कि n के कॉरस्पॉन्डिंग आइगन वैल्यूज अलग अलग है। तो यहां पर भी देखो क्या किया गया है इस सॉल्यूशन में, माने हर n के कॉरस्पॉन्डिंग एक एनर्जी है, तो कॉरस्पॉन्डिंग वेव फंक्शन में भी n का डिपेंडेंस होगा, तो इस पे भी एक n का डिपेंडेंस देके और इसको लिखा गया है hn, where the function hn are polynomial of order n. Moreover, the polynomial hn satisfy the Hermite equation with lambda equals to 2n plus 1. So ये Hermite equation लिखा गया, और जब Hermite equation ये completely बन ही गया है तो उसका स्टैंडर्ड सॉल्यूशन को हम लोगों ने डायरेक्ट लिख दिया है। हम एक्चुअली लास्ट दिन इसी के लिए एक पेज देंगे बोले थे कि कैसा इक्वेशन है, क्या उसका जेनरेटिंग फंक्शन है, क्या उसका रोड्रिग्स फॉर्मूला है, ये दे देना चाह रहे थे, बट अनफॉर्चुनेटली आई कुड नॉट लोकेट दैट पेज जिसमें ये सारा चीज बना हुआ था। सो ओके, दिस इज द थिंग, एंड फॉर डिफरेंट वैल्यूज ऑफ n, Hermite polynomial of zero order, Hermite polynomial of first order, second order, don't be fear of these things. इसमें एक इंटरेस्टिंग फैक्ट आपको ये बताएं कि बहुत सारे एग्जाम में, एंट्रेंस एग्जाम में ये सब वैल्यूज डायरेक्ट पूछता है। व्हाट इज द वैल्यू ऑफ h2 जीटा, Hermite polynomial of second order, उसका वैल्यू क्या होगा? तो you just need to know the generating function. This is the generating function. इसमें आपको n का वैल्यू सब्स्टिट्यूट करके लिखना है, ओके तो इसमें आपको n का वैल्यू सब्स्टिट्यूट करके लिखना है, लेकिन हम इसमें फिर से गलत लिखे हैं। मैं देखो तो क्या है, क्या गलत लग रहा है यहाँ पर? Anyone, if you can detect any error? Anyone, if you can detect any error here? यहाँ पर एक्चुअली ये फर्स्ट डेरिवेटिव लिख के छोड़ दिया गया, ये एक्चुअली nth डेरिवेटिव है। अगर nth डेरिवेटिव नहीं होगा तब तो खाली इससे प्लस माइनस ही ना बदलेगा, बाकी तो सब सेम आ जाएगा, isn't it?
Yes,
यहाँ
sir.
पर ये n का वैल्यू मिस कर दिया था। nth डेरिवेटिव, सपोज यू टेक n इक्वल्स टू 0, ऐसे एक तो वैल्यू रख के देखो तो हम ठीक लिखे हैं कि नहीं पता चल जाएगा। n इक्वल्स टू 0, दिस बिकम्स
1.
1. n equals to 0 means this derivative is not present, that also becomes 1.
Yes, sir.
Now you have this exponential plus zeta square and exponential minus zeta square. ठीक है,
Yes, sir.
लेकिन एक और वेरीफाई करेंगे नहीं तो पता नहीं चलेगा। सपोज n is 1, so you have minus 1 exponential zeta square. Which order of derivative? फर्स्ट ऑर्डर।
First order.
तो फर्स्ट ऑर्डर डेरिवेटिव, इसको डिफरेंशिएट कर लो, एक्सपोनेंशियल माइनस जीटा स्क्वायर इनटू -2 जीटा।
Yes, sir.
So these two clubbed will become 1, and this minus will become positive, so you have 2 zeta. So from this generating function, many a times this question is being asked that write the value of this Hermite polynomial, and I am also concerned with this. Why? Because changing the value of n will give me different eigenvalues, and changing the value of n will also give me the wave functions. तो हमको पुट कर करके तो उसका वैल्यू चाहिए। So the complete normalized wave function, this is our possible wave function. तो पॉसिबल वेव फंक्शन में सॉल्यूशन सब पुट करके और एक तो फाइनली इसमें नॉर्मलाइजेशन कांस्टेंट लगा दिया गया। नॉर्मलाइजेशन कांस्टेंट को कैलकुलेट करने का ये इक्वेशन है, किसी को कैलकुलेट करने का आपको जरूरत नहीं है। कैलकुलेट करने से ये नॉर्मलाइजेशन कांस्टेंट का वैल्यू इतना निकल के आएगा और ये इसका कंप्लीट वेव फंक्शन है। ठीक है, ये आपको कंप्लीट वेव फंक्शन है। यू नीड टू रिमेंबर दिस, इसको आपको याद करना ही होगा सभी तरह के एग्जाम के लिए, फॉर योर सेमेस्टर एग्जाम, फॉर योर एंट्रेंस एग्जाम, दिस वन एंड द एनर्जी आइगन वैल्यू, दिस वन. Now once we are ready with this eigenfunction and eigenvalues, then I will start the meaning of these results. That is what we are targeting. इसका जो मीनिंग पार्ट है, इसका वेव फंक्शन का पार्ट है, कैसे क्लासिकल ऑसिलेटर डिफर करेगा फ्रॉम अ क्वांटम ऑसिलेटर, वेव फंक्शंस का इंटरप्रिटेशन, तो बहुत सारा चीज है इसमें, बहुत इंटरेस्टिंग चीज है. जो कैलकुलेशन वाला पार्ट है दैट इज ओवर, सो वी कैन start with the meaning part of this. So what you will do is, because you have another class scheduled, so I will have the next class again tomorrow. I will send this calculation right now only. After whatever class you have next, इसके बाद के क्लास के बाद थोड़ा सा मैथमेटिक्स को देख लेंगे. Don't bother about these things. ये अभी डिस्कस होना बाकी है, एकदम डिटेल में करेंगे. यही फिजिक्स है, इसी को समझाने के लिए इतना कैलकुलेशन किए हैं. इन सब को एकदम प्रॉपरली समझाएंगे, ऐसे देखने से नहीं क्लियर होगा. और हम लोग बुक से देख के करेंगे भी नहीं, हम लोग इसको खुद से ड्रॉ करेंगे. एक दो हमने पेज इसलिए रखा है कि 4-5 ड्रॉ करने में टाइम लगता है, तो हम 1-2 आपको समझाएंगे कि कैसे आ रहा है, और बाकी को देखने से आपको हेल्प मिल जाएगा, इसलिए रखा गया है. और इसमें एक लास्ट वाला देखोगे, n equals to 20 के लिए भी बनाया गया है. एंड इट इज नॉट दैट n equals to 20 जस्ट फॉर्मेलिटी के लिए बनाए हैं. लार्जर वैल्यूज ऑफ n पर सिस्टम का बिहेवियर अलग है, लोअर वैल्यूज ऑफ n पर सिस्टम का बिहेवियर अलग है. इसीलिए एक लार्जर वैल्यू ऑफ n को भी डिस्कस करने का कोशिश किया गया. ओके, एंड ये सारा इंटरप्रिटेशन ना बहुत सारे बुक से ओवरऑल मिलाकर बनाए हैं. इट इज नॉट कि एक ही जगह पर आपको सारा चीज रेडिली अवेलेबल है, तो बहुत सारा बुक से सबको मिलाकर हम लोग बनाए हैं. सो वंस वी विल बी ओवर विद दिस, तो फिर इसका टाइम इवोल्यूशन पर भी जाएंगे. इज इट ओके?
यस सर.
ठीक है, इसमें ये ध्यान रखना, ये सब क्लास का लेकिन अटेंडेंस बन रहा है, हम सॉफ्टवेयर के थ्रू अटेंडेंस नोट कर ले रहे हैं. तो फिर बाद में मत बोलना कि मेरा अटेंडेंस कम हो गया, उसके लिए हम रेस्पॉन्सिबल नहीं रहेंगे. सो अपने क्लास में ये बात बोल दीजिएगा, क्योंकि 3-4 बच्चा आज एब्सेंट है, टोटल 5 बच्चे एब्सेंट है आज. तो वो सारे लोग अपना रेस्पॉन्सिबिलिटी खुद लेंगे. पढ़ाई तो पढ़ लेगा, ये हम मान ही रहे हैं, लेकिन क्लास का कमी हो गया तो वो उसकी रेस्पॉन्सिबिलिटी होगी. तो डू मेंशन दैट. तो आई विल जस्ट नाउ सेंड यू द आंसर. यू गो थ्रू द मैथमेटिक्स वंस अगेन. इंश्योर करो कि एग्जाम में आए तो हम कम से कम लिख पाए. फिजिक्स हम आपको समझाएंगे, कल जैसे ही क्लास करेंगे आपको 100% उसका फिजिक्स वाला पार्ट समझ में आ जाएगा कि क्या पढ़ रहे थे, क्यों क्वांटम वाला पढ़ने का जरूरत है, क्यों क्लासिकल वाले से अलग है. एंड फॉर्चुनेटली एनफ ये एटॉमिक वाला पार्ट पहले तिवारी सर पढ़ाते थे, लेकिन इस बार क्योंकि उनके अवेलेबिलिटी नहीं है, तो थोड़ा सा जो लास्ट का पार्ट है एटॉमिक वाला, जीमान इफेक्ट एक्सेट्रा, वो भी हम डिस्कस करेंगे. तो हम इन सब बातों के साथ उसको कोरिलेट भी करेंगे, यहाँ जो पढ़ रहे हैं उसके साथ उसको कोरिलेट करेंगे कि देखो ऐसा आया था, इसलिए एटॉमिक फिजिक्स में ऐसा हो रहा है. सो रिजल्ट्स के फिजिकल मीनिंग पर फोकस बहुत जरूरी है. ठीक है, फाइन, ओके.
थैंक यू सर.
यस, वेलकम.
Thank you,
थैंक यू
sir.
सर.